Well, in the last lecture, we have defined differentiation and we have seen the algebra of derivatives as well as chain rule. So, now sometimes it may happen that if we had been given a function f of x equal to something, then like for example, y equal to f of x, then we can take the derivative with respect to x. In real life, we might need to face the situation where we cannot explicitly write y in terms of x. For example, look at the this graph. This is called folium and it is given by the algebraic equation x q plus y q, let us say minus 9 of x y is equal to 0. Now, here as we know that this curve is not a graph of a function, because we know the straight line rule of when the curve is going to be a graph of a function. So, basically we cannot find out y prime by writing it y is equal to something in terms of x. So, how to handle this situation? Let us take for example, a easy example. Let us say circle x square plus y square is equal to r square. Here of course, we can write y in terms of x. Now, if we try to do this, then this is going to be y is equal to plus or minus square root of r square minus of x square. This is a circle at center 0 0 and radius r. So, both x is minus of r to r may be included. Okay. So, now let us define a function f of x which is equal to square root of r square minus of x square and g of x, this is equal to minus of square root of r square minus of x square. Now, if we calculate f prime of x, then this is going to be by chain rule, this is 1 by 2 square root of r square minus of x square into minus of 2 x, which is equal to x by square root of r square minus of y square or minus of x by r square minus of x square. Similarly, here if we write g prime of x, this is again going to be minus 1 by 2 square root of r square minus of x square into minus of 2 x, which is equal to x by square root of r square minus of x square. So, this I can write it as minus of x by f of x, when x if I take in minus of r to r, and here also this is equal to minus of x by g of x. Therefore, y is equal to plus or minus x. It does not matter if I write y prime to be minus of x by y. This is what we are getting. Okay. So, now this we can solve it even without explicitly writing down y in terms of x. How? Let us look at this. I have x square plus y square is equal to r square. Then if I take the derivative, both sides, we get 2 x plus 2 y, again chain rule, and then this is y prime which is equal to r is a constant which is equal to 0. This implies that y prime is equal to minus of x by y. So, this is called the implicit differentiation. Even when we get certain function, then without writing y is equal to in terms of explicitly in terms of x, still we can get the derivative. For example, let us consider another example. This is if 2 y is equal to x square plus sin y. Now, we want to find the derivative, and as we can see, we can't separate y, we cannot write y in term explicitly in terms of x. However, if we take the derivative both the side, this will imply that 2, then this is y prime, this is 2 x, then this is cos y into y prime. So, this implies that y prime then 2 minus of cos y, this is equal to 2 x. This implies that y prime is equal to 2 x by 2 minus cos y. This can never be 0, whatever the value y takes, cos is going to be between minus 1 and 1. So, this is called so called implicit differentiation. Now, of course, when we had been given with a function f from I to r, then f differentiable on I, then f prime is also going to be a function from differentiable on I, then f prime is again a function from I to r. Now, what can we say about f prime? Is f prime going to be differentiable again, and will f prime be continuous? So, these are the question what one would like to ask. So, now let us take for example, f of x which is equal to x square by 2 if x is greater or equal to 0, and minus of x square by 2 if x is strictly less than 0. Now, this is of course, for x greater than not equal to 0, this is a polynomial, f a polynomial. Hence, differentiable. Now, at x equal to 0, we need to look at f of 0, let us say x 0 plus, then this is f of x minus of f of 0 divided by x minus of 0, which is equal to f of x is limit x tends to 0 plus, this is x square by 2, f of 0 is 0 divided by x, which is equal to 0. Similarly, limit x goes to 0 minus f of x minus f of 0 by x minus of 0, this is equal to limit x goes to 0 minus of x square by 2 divided by x, this is again is going to be 0. So, f this function f is differentiable at 0 and f prime of 0 is equal to 0. This will imply that f prime at 0 is equal to 0. Then what is f prime of x is equal to x if x greater than 0, is equal to minus of x if x less than 0, is equal to 0 if x is equal to 0. And what is this curve? This function is nothing but so f prime of x is nothing but mod x, and we know that mod x is not differentiable at 0, and f prime is a function from R to R, but it is not differentiable where f is differentiable. So, it is not necessarily true that if a function is once differentiable, then the derivative is also again differentiable. Then it will be little more involved if we want to find a function such that f prime is not going to be continuous. Now, let us look at the function f of x, which is equal to x square sin 1 over x if x is not equal to 0 and equal to 0 if x is equal to 0. Now, obviously, if x is not equal to 0, then x square is differentiable and sin 1 over x is differentiable, sin x is differentiable. By the chain rule, f compose sin 1 over x is differentiable, and so x square sin 1 over x is also differentiable. So, f is differentiable, and f prime of x we can write it by the product and the chain rule 2 x sin 1 over x plus x square into cos 1 over x, and then 1 over x derivative is 1 over minus 1 over x square. So, this is equal to 2 x sin 1 over x and minus cos 1 over x. Now, if at x equal to 0, this is limit h goes to 0, h square sin 1 over h by h, which is equal to limit h goes to 0, h sin 1 over h. By sandwich theorem, we have seen that this limit is nothing but going to be equal to 0. So, f prime of x is equal to 2 x sin 1 over x minus cos 1 over x if x not equal to 0 and 0 if x is equal to 0. And as you can see that at 0, this function f prime, which is defined all over, is not continuous, because cos 1 by x actually it oscillates, this first part goes to 0, and in the second part the cos 1 over x it oscillates so much that it will not have a limit as x goes to 0. So, f prime is not continuous at x is equal to 0. So, here is a function which is differentiable everywhere, and then the f prime is not continuous. One of the very interesting thing about this sort of function, which I am not going to give you a proof, but what we have seen is that if f is a continuous function, then it satisfies intermediate value property, but it is not a necessary condition for to satisfy the intermediate value property. However, if f is differentiable, whether f prime is continuous or not, f prime will always satisfy intermediate value property. So, this I will not prove it, this is a fact which I just want to state, which is a very interesting fact. Now, we have talked about if f differentiable on I, then an interval, then f prime is a function from I to R. We can talk of the derivative of f prime. So, the derivative if f prime is differentiable, then the derivative of f prime is denoted by f double prime, and clearly f double prime of x equal to limit of h goes to 0, f prime of x plus h minus of f prime of x divided by h. So, now f prime is again a function. If f double prime is also differentiable, then we can talk of the derivative of f double prime. We will denote it by f triple prime, so on and so forth. And sometimes you will find various symbol. For example, you can find if y Leibniz symbol y equal to f of x, then you have y prime, then you, or this is dy by dx. In some book you will find y dot, then also you can have y double prime, then this is d square y by dx square, which is equal to derivative of dy by dx, because dy by dx is again a function of x. So, we can talk of if it is differentiable, then we can talk of the derivative of that, and some you put like this. So, in general we write f n is the nth derivative of f, and d n y by d x n, this is equal to d by dx. You see, all these higher derivative will not automatically, they will not exist if f prime exists, but if they are differentiable, as long as they are differentiable, we can take the derivative. For example, you take a polynomial f of x equal to a 0 plus a 1 x plus a n x to the power n, then this polynomial derivative is the first derivative will exist and then it is again going to be a polynomial, second derivative will exist, it is again going to be a polynomial, so on and so forth. So, this is going to, for any n we can define the derivative of this function. As you can see that if suppose if I take the first derivative, then a 0 goes away, a 1 becomes the constant term. If I take the second derivative, then a 1 will go away, it will start from a 2. If I take nth derivative, only a n is going to be there, and this is equal to 0 if n is strictly bigger than n, because you at nth derivative you are going to land up in the constant term a n, and then if you take the derivative of this constant, you are going to get 0, and then this is this for polynomial, this is going to have derivative everywhere. Similarly, for example, suppose f of x is equal to sin x, then f prime of x is equal to cos x, and f double prime of x is equal to minus of sin x, and f triple prime of x is equal to minus cos x, and f fourth derivative of x, this is going to be equal to cos x is minus sin x. So, this is going to be sin x, f fifth would be cos x, so on and so forth. So, you would like to write down f n of x, this is equal to minus 1 to the power k, then this is going to be sin x or cos x. So, now it will be a good exercise for you to figure out what the sign of this derivative is, and then when you are going to get sin x or cos x. Nevertheless, this function is differentiable, f of x equal to sin x for any nth order derivative of sin x exists. So, now we will, after doing this, so let us try to see some of the applications of the derivative, actually we will see this derivative will tell us about various behavior of our function, and it will also help us to find the maximum and the minimum value of the function. But nevertheless, first let us try to see that if f from a b closed interval a b to r is a continuous function, then f is bounded. This is a fact. I will give you the proof. So, in the first attempt, if you are not getting the proof, that is fine, but this fact is very important. If f is a continuous map from a closed and bounded interval, then f is bounded. That means what? There exists, that is, there exists a m such that mod of f of x is lesser equal to m for all x belongs to a b. In other words, the range set of f is a bounded set. Now, the proof is very interesting. So, now suppose f is not bounded. Now, I have an interval a b. Then, if I divide the a b, this is, let me call this as a plus b by 2. I divide this interval into two parts. So, it may happen that either at least in one of these sub intervals f is unbounded. If f is bounded on this interval, as if f is bounded on a plus b by 2 and a plus b by 2 to b, then obviously f is going to be a bounded function on closed interval a b. So, f is not bounded means at least in one of these interval f is not bounded, one of these sub interval. Well, so we can assume let f is not bounded on a to a plus b by 2. Okay. So, in now again I divide it a to a plus b by 2 f, where f is not bounded. I have an interval, I divide it into two parts. Then either f is not bounded here or f is not bounded here. It cannot happen that f is bounded on both the intervals, then f will automatically be bounded in this whole interval. Suppose it is not bounded here, then again I divide it. So, either f is not bounded here or f is not bounded there in the other interval. So, one of these two sub interval f is not bounded. So, I continue this process. So, let me get that let a 1 b 1 be the first sub interval, f is not bounded means unbounded, and I will take a 2 b 2, which is again I divide it by I divide a 1 b 1 divide 2 equal sub interval, then a 2 b 2 is the f is unbounded on a 2 b 2. So, I continue like this. So, I will get a n b n f unbounded. A to B to I again divide it into two equal parts. In one of I will choose the choose one part in which f is unbounded. Every step I am going to get that f is unbounded in some sub interval, and as you can see this b n minus of a n, b 1 minus of a 1 is b minus a by 2. Now, this b 2 minus a 2 is equal to b 1 minus a 1 by 2, which is equal to b minus f a by 4. So, this is b minus of a by 2 to the power n. This is what we have got. Now, we consider the left all the left end point a 1, a 2, a is equal to a 1 in this case, a 3. Now, this is a bounded set. So, therefore, this is contained in R, a bounded set. So, then you take the supremum of A is equal to alpha, the supremum is going to exist. Now, f is continuous and this belongs to A B and f is a continuous function. Therefore, f is continuous, this will imply that there exists a delta greater than 0 such that for x belongs to alpha minus delta, alpha plus delta, I put this in A B, will imply f of x minus of f of alpha, this is mod of f of x is less than 1. This will imply that mod of f of x is less than 1 plus mod of f of alpha, which is a finite number independent of x. I can put alpha minus a n b n, I can make it too small such that it is going to contain inside alpha minus delta to alpha plus delta. Therefore, for every x in this a n b n, you choose n large. Then f of x is f is bounded, which is a contradiction. Therefore, so forget about the proof, but the fact is that if f is a continuous function on closed and bounded interval, then f has to be bounded. Okay, so thank you. So, we will continue with this studying the property of functions using derivative.